Have you ever wondered if the most intricate theories about the universe might challenge us to view reality from an entirely fresh perspective? Some scientific ideas are not just fascinating, they can be downright unsettling, as they have the potential to reshape our understanding of the cosmos and our role within it. How did the universe come into existence? Why do we perceive it the way we do? For centuries, various theories have sought to unravel these enigmas, and some are far from comforting. Could there be parallel universes coexisting alongside our own? Today we'll delve into some of the most captivating theories concerning space, time, and the universe, including the famous space-time concept introduced by Einstein, which has left scientists and experts alike in a state of bewilderment due to its complexity. Let's kick things off with the multiverse theory. This hypothesis suggests that our universe isn't singular but is part of a larger ensemble known as the multiverse. This ensemble would encompass countless universes, each possessing its own matter, energy, space, and time. The notion of the multiverse isn't a modern invention. In fact, it has been discussed for over 2,500 years, dating back to the philosophers of ancient Greece. Anaximander in the 6th century BC was among the first to propose the possibility of multiple worlds, but it was the atomists like Democritus and Epicurus who further developed the idea of infinitely coexisting worlds. Over the years, this theory has evolved alongside cosmology, physics, and philosophy. Nowadays, some scientists view the multiverse more as a philosophical idea rather than a traditional scientific theory, since it cannot be tested or falsified through empirical experimentation. However, other researchers have sought evidence that might hint at the existence of alternate universes. Before we continue exploring the fascinating theories of the universe, take a moment to like this video and subscribe to our channel. This helps us keep producing relevant content that bridges science and spirituality, expanding our horizons together. Within the scientific community, the multiverse theory has its proponents and critics. Detractors argue that its unverifiability and unfalsifiability make it unsuitable for rigorous scientific inquiry. Nonetheless, physicists like Max Tegmark and Brian Greene have categorized different levels of the multiverse. Level 1 posits that alternative universes are expansions of our own, while Level 2 suggests that these universes could coexist with differing physical constants. Level 3 is based on interpretations of quantum mechanics, and Level 4 encompasses the idea of a mathematical universe which seeks to explain all cosmic phenomena through a unified theory. In the previous segment, we delved into the intriguing multiverse theory, which categorizes universes into 4 distinct levels. Now, let's shift our focus to another equally perplexing concept, the simulation theory. This idea suggests that everything we know, ranging from matter to our personal experiences, might merely be an incredibly advanced simulation, akin to a computer program. In simpler terms, we could be living within a simulated reality, crafted by a technologically superior civilization. What distinguishes this simulation from virtual reality is one crucial aspect. While virtual environments are clearly identifiable as artificial, a simulation at the level of the universe would be so realistic that it would be nearly impossible to differentiate it from authentic reality. This is the core of the theory proposed by Swedish philosopher Nick Bostrom, who in 2003 argued that an advanced civilization might consciously simulate entire realities inhabited by beings unaware of their simulated existence. The notion of a simulated reality isn't entirely new. It has been contemplated within various philosophical traditions, both Western and Eastern. Plato, through his allegory of the cave, suggested that our perceptions might not represent the ultimate reality. Similarly, in Chinese philosophy, Zhuangzi pondered the fine line between dreams and reality. Yet it was the film The Matrix that popularized this unsettling idea in contemporary culture, portraying a humanity ensnared in a simulation. Bostrom took it a step further by positing that the likelihood of us existing in the fundamental reality is exceedingly low, 1 in billions, to be precise. Even influential figures like Elon Musk have supported this notion, asserting that if future civilizations develop sufficiently advanced computing technology, the creation of simulations would become an inevitable choice. However, this theory has sparked intense debate. On one hand, physicists and philosophers have engaged in discussions about the feasibility of detecting whether we reside within a simulation. For instance, Ho-Man Ho from the California Institute of Technology stated that if a simulation possesses infinite computing power, it would be impossible to determine our existence within it. Conversely, if computational limits exist, there might be clues indicating the simulated nature of our world. On the other hand, some scientists have been quite critical. German theoretical physicist and science communicator Sabine Hossenfelder labeled the simulation theory as pseudoscience, while cosmologist George Ellis regards it as technically unviable. Both argue that such debates belong more in the realm of science fiction than in serious scientific discourse. Einstein's general theory of relativity ushered in a paradigm shift regarding the nature of the universe. It revealed that space-time bends under the influence of the mass of galaxies, stars, and planets, a concept that many scientists found difficult to accept. In fact, it took over 40 years to fully grasp black holes, and only recently has in-depth research into white holes begun, as noted by theoretical physicist Carlo Rovelli from the Center for Theoretical Physics in France. Perhaps we will require less time to understand this perplexing cosmic phenomenon. Now let's dive into the superfluid space-time theory, another astonishing concept. Also known as superfluid vacuum theory (STAT, it posits that the physical space we inhabit behaves like a superfluid. A superfluid is a state of matter with extraordinary properties. It experiences no resistance to flow, possesses no viscosity, and can flow indefinitely. This behavior is associated with the phenomenon of Bose-Einstein condensates, where particles act as a unified whole at extremely low temperatures. Applied to space-time, the idea of a superfluid suggests that instead of viewing the vacuum as inert nothingness, we might envision space itself as having an underlying structure akin to a quantum fluid. This quantum fluid could be responsible for the gravitational effects we observe throughout the cosmos. Some theorists argue that this model may help elucidate certain phenomena that remain incompletely understood, such as dark energy and the accelerated expansion of the universe. Superfluid space-time theory implies that the universe might exhibit more complex behavior than we previously imagined, opening avenues for new understandings of the interplay between gravity and quantum mechanics. This connection between the infinitely large and the infinitely small could be crucial for a unified comprehension of the laws governing the cosmos. However, like many theories in modern physics, much remains to be validated before this idea can gain widespread acceptance. In the 1920s, Albert Einstein and Indian physicist-mathematician Satyendra Nath Bose published a paper discussing the properties of light photons. Bose established specific rules to determine whether two photons should be regarded as identical or distinct, and Einstein applied these same rules to the atoms of a gas, contemplating how they would behave under such conditions. They discovered that at extremely low temperatures, most atoms occupy the same quantum state, the lowest energy state possible. This phenomenon, known as Bose-Einstein condensate, describes the aggregation of particles in a state of minimal energy. In 1995, American physicists Eric Cornell and Carl Wieman achieved, for the first time, the cooling of atoms to their lowest energy level, just 1 million degrees Kelvin above absolute zero. This remarkable feat earned them the Nobel Prize in Physics in 2001. The temperature achieved in Cornell and Wieman's laboratory was significantly lower than any temperature detected in outer space. The Bose-Einstein condensate they obtained is a superfluid, a state of matter that is entirely devoid of viscosity. This means that if placed in a closed circuit, this superfluid could flow indefinitely without losing energy due to friction. Interestingly, there exists a theory suggesting that space-time might behave as a superfluid with similar characteristics. According to the general theory of relativity, space-time is a mathematical model that combines the three spatial dimensions with time into a single four-dimensional continuum. Within this framework, all physical events in the universe occur. However, Luca Mazzone from Ludwig Maximilian University and Stefano Liberati from the International School for Advanced Studies propose that space-time is not merely a reference frame in which physical objects, like galaxies and stars, exist. They argue that space-time is a physical substance in its own right, akin to a vast ocean. According to this hypothesis, just as water is composed of countless molecules and atoms, space-time may contain microscopic particles at a level of reality deeper than we can currently detect with our instruments. This theory suggests that space-time acts as a superfluid with zero viscosity. One of the most fascinating properties of these fluids is that, instead of behaving like a conventional liquid that gains mass when agitated, they separate into vortices. In the case of superfluid space-time, these vortices could serve as the starting points for galaxy formation. Now let's explore the Cyclic Universe Theory, a cosmological model proposed by South African physicist Neil Turok and American theoretical physicist Paul Steinhardt. Its theory draws inspiration from the concept of ekpyrosis in ancient Stoic philosophy, which means conflagration or conversion into fire. According to the Stoics, Ekpyrosis is a cosmic fire that encompasses everything and represents the contraction phase of an eternal cycle of destruction and rebirth. The ekpyrotic model suggests that instead of beginning from a singularity as proposed by the Big Bang, the universe emerged from the collision of two branes, hypothetical physical entities within the framework of string theory, or the theory of everything, which seeks to unify the four fundamental forces of physics: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. The ekpyrotic hypothesis posits that the universe is trapped in an eternal cycle of birth, cooling, and rebirth through a fiery phase. This model seeks to address one of the great mysteries that the inflationary theory of the Big Bang fails to resolve: what happened before the grand explosion. The explanation offered by the ekpyrotic theory is that what we refer to as the Big Bang was actually a significant re-expansion, representing a transition from a prior period of contraction to the current phase of cosmic expansion. According to this cyclical approach, the most crucial events that shaped the universe occurred before this expansive phase, and the cosmos continues to repeat this cycle of expansion and contraction at regular intervals. Similar to inflationary models, this theory accurately describes the key characteristics of the observable universe, predicting a uniform distribution with both hotter and colder regions, which aligns with observations of the cosmic microwave background, CMB. This radiation background is considered compelling evidence of the Big Bang, but proponents of the ekpyrotic model argue that it is also compatible with their notion of a cosmic bounce. A new advantage of the ekpyrotic theory is that it circumvents the emergence of a multiverse, a concept that has posed challenges for inflationary models. And quantum fluctuations are incorporated into the inflationary theory. Difficulties arise in explaining how the universe attained the observable uniformity. However, the cyclic hypothesis, by relying on different principles, does not encounter such complications. Despite its merits, the ekpyrotic theory has also faced several criticisms. One of the main critiques is that it relies on essential elements of string theory, which posits that subatomic particles are not points but rather vibrational states. This concept, while intriguing, is not widely accepted across the scientific community. Additionally, questions arise about what truly occurs when two branes collide, an aspect that the theory has yet to clarify entirely. Now let's turn our attention to the Bang theory, which remains more than 90 years after its proposal the most widely accepted explanation for the origin of the universe. Initially formulated by Belgian priest and scientist Georges Lemaitre, the Big Bang theory is supported by two fundamental observations: the cosmic microwave background and the expansion of the universe. This theory posits that the universe emerged from an extremely dense and hot point that gave rise to space, time, and matter. In his early publications, Lemaitre referred to this phenomenon as the primeval atom. The term Big Bang was ironically coined by English astrophysicist Fred Hoyle, who used it during a BBC radio broadcast in 1949, attempting to mock the concept. According to the Standard Model, the Big Bang occurred approximately 13,800,000,000 years ago. While this model does not aim to explain what triggered the grand explosion, it provides a detailed account of how the universe has evolved from its earliest moments to around 300,000 to 400,000 years later, when atoms began to form and the universe became transparent enough to allow background radiation to escape. Before we continue exploring the fascinating theories of the universe, take a moment to like this video and subscribe to our channel. This helps us keep producing relevant content that connects science and spirituality, expanding our horizons together. Additionally, I invite you to delve deeper into your inner journey by downloading our e-book, Divine Essence: Rediscovering the Inner Self and Spiritual Peace. The link is in the description, and this material will assist you in advancing on your path toward balance and inner peace. The Big Bang model remains the predominant cosmological theory to explain not only the origin but also the large-scale evolution of the universe. According to this hypothesis, in its early stages, the cosmos existed in a state of incredibly high density and temperature. From this point, the universe began its expansion process, a phenomenon that continues to this day. Following its initial expansion, the universe cooled sufficiently to allow for the formation of the first subatomic particles and subsequently atoms. These particles grouped together under the influence of gravity, forming massive clouds of matter that eventually led to the creation of planets, stars, galaxies, and other cosmic structures. Once the universe began this cooling process post-Big Bang, evolution followed well-established principles of particle physics, even though this phase of progressive expansion and cooling is no longer strictly part of the Big Bang Theory itself. Since it was deduced that an expanding universe must trace back to a singular point of origin, most scientists embraced the idea of an explosive cosmic beginning. This concept was solidified when in 1929, astronomer Edwin Hubble concluded that galaxies were moving away from each other, based on the analysis of their redshifts. The Big Bang Theory ultimately surpassed the steady-state theory, a hypothesis initially defended by Fred Hoyle, who ironically coined the term Big Bang to ridicule this specific idea. The steady-state theory, proposed as an alternative to the Big Bang, asserted that while the universe was expanding, the resulting decrease in density from this expansion was offset by the continuous creation of matter. This theory was based on the perfect cosmological principle, which states that the universe should appear identical to any observer, regardless of their location in space. Furthermore, this principle encompasses the time dimension, meaning the universe should look the same from any place and at any time. The first to propose a steady-state cosmology was British physicist and astronomer James Jeans in the 1930s, who suggested the idea of continuous matter creation. In 1948, this notion was revisited and expanded upon by Fred Hoyle, Thomas Gold, and Hermann Bondi. Initial calculations showed that a static universe was incompatible with the theory of general relativity, and Hubble's observation of the universe's expansion also seemed to contradict this proposal. Nevertheless, supporters of the steady-state theory accepted that the universe was expanding, but argued that the density of the cosmos remained constant over time. However, problems with this hypothesis began to emerge in the late 1960s. Observations revealed that the universe was changing, particularly with the detection of quasars only in the most distant galaxies and not in those closer to us. This phenomenon suggested cosmic evolution over time, contradicting the idea of an eternal and unchanging universe. The most decisive blow against the steady-state theory came in 1965 with the discovery of the cosmic microwave background. In a steady-state universe model, there would be no reason for the existence of background radiation with thermal characteristics. Explaining this radiation within the framework of the steady state would necessitate assuming the presence of millimeter particles in intergalactic space that would absorb radiation emitted by extremely bright galactic sources, complicating the model significantly. Despite being a widely discredited hypothesis, the steady-state theory still has some notable defenders. So one of them is Indian astrophysicist Jayant Narlikar, who, in collaboration with Fred Hoyle, formulated the Hoyle-Narlikar theory. This theory attempts to synthesize Einstein's principles of relativity with Mach's principle, proposing a modified version of the steady-state model that some cosmologists still consider viable. Now let's move on to the Goldilocks planets theory. This term, inspired by the tale of Goldilocks and the Three Bears, is used to describe exoplanets located within the habitable zone of a star system. In this story, Goldilocks always chooses the middle option, not too hot and not too cold, reflecting the ideal location of a planet to support life. In astronomical terms, a Goldilocks planet is situated at a distance from its star that allows for favorable conditions for life as we know it. For instance, within our own solar system, neither Mercury nor Pluto can be classified as Goldilocks planets, as one is too close to the Sun while the other is too far away. The planets located in this habitable zone are of significant interest to scientists as they represent a potential opportunity for the search for extraterrestrial life or, in the future, for human colonization. The detection of Goldilocks planets outside our solar system has played a crucial role in refining the Drake equation, a formula designed to estimate the number of intelligent extraterrestrial civilizations in our galaxy. One of the key parameters of this equation is the fraction of planets in habitable zones. If the numbers of these planets turn out to be low, it would support the rare Earth hypothesis, which posits that life on Earth is the result of a series of extremely improbable circumstances. Conversely, if the number is high, it would lend credence to the Copernican mediocrity principle, suggesting that Earth is neither unique nor special. One of the main objectives of the Kepler mission, a space telescope launched by NASA in 2009, was precisely to search for Goldilocks planets. Before the mission concluded in 2018 due to fuel depletion, the data collected by Kepler indicated that there could be over 40 billion planets in habitable zones within the Milky Way, with approximately 11 billion of them potentially orbiting Sun-like stars. These figures suggest that an Earth-like planet could be as close as 12 light-years away from our solar system. Finally, we arrive at the sterile neutrino theory. The neutrino, whose name derives from Italian and means little neutron, is a neutral subatomic particle with a known angular momentum called spin. Discovered in 1956, this particle has been a subject of controversy since then, particularly regarding its mass. Initially thought to be massless, experiments conducted in Canada and Japan in the early 21st century demonstrated that, although extremely small, neutrinos do possess mass equivalent to 1/millionth that of a hydrogen atom. The sterile neutrino theory proposes the existence of a variant of neutrinos that do not interact with 3 of the 4 fundamental forces of the standard model of quantum physics. While regular neutrinos interact via the weak nuclear force, sterile neutrinos would only be influenced by gravity. These hypothetical neutrinos would be challenging to detect due to their lack of interaction with electromagnetism, the strong nuclear force, and the weak nuclear force. The term sterile is used to differentiate these hypothetical neutrinos from the ordinary neutrinos of the standard model, which participate in weak interactions. These common neutrinos exhibit what is known as left-handed chirality, meaning they only interact via the weak nuclear force. In contrast, sterile neutrinos are hypothesized to have right-handed chirality, implying they do not interact through known forces, except possibly gravity. The search for sterile neutrinos is one of the most active fields in particle physics, as their discovery could help resolve some of the greatest mysteries of the cosmos, such as dark matter. This type of matter, believed to be the most abundant in the universe, is termed dark because it does not interact with the electromagnetic field. Consequently, it neither emits, reflects, nor absorbs light, making it extremely difficult to detect directly. However, sterile neutrinos could play a role in explaining this mysterious matter, as well as phenomena such as baryogenesis and the hypotheticatism, the magnetism, a theoretical form of electromagnetism associated with dark matter. In 2018, the American experiment Mini-Buni generated significant excitement by announcing possible indications of sterile neutrinos. However, 3 years later, no conclusive evidence has been found to confirm the existence of this particle. As one physicist remarked, assuming it exists, we are still searching for how to detect it unequivocally. If some of the topics discussed in this video, such as general relativity, seem complex, don't worry. Even Niels Bohr, a close friend of Einstein and Nobel laureate in 1922 for his contributions to atomic understanding and quantum mechanics, acknowledged the difficulty of explaining some of these concepts. A famous anecdote recounts that when a student asked Bohr to explain general relativity simply, Bohr replied that if he ever found someone who could explain it easily, he should immediately come to share that explanation with him. After all, general relativity is regarded as one of humanity's greatest intellectual achievements. We hope this video has been helpful in clarifying some of these scientific mysteries. If you have anything to add or any questions, feel free to share your thoughts in the comments. Please like this video and share it with your friends and family so they can also learn more about these fascinating theories of the universe. Remember, as it is often said, a people that does not know its history is condemned to repeat it. This video serves as a reminder that beyond our everyday perception of reality, there exist deeper and more mysterious dimensions that often elude our understanding. Science offers us captivating theories about the nature of the cosmos, such as the possibility of a multiverse, or the unsettling idea that our reality might be simulated. However, these ideas are not merely abstract scientific concepts. They also invite us to reflect on our own existence and our place in the vast and enigmatic universe. Just like science, spirituality seeks to explore the deeper truths about who we are and what our purpose is. They urge us to look beyond the surface of things, to question what we believe we know, and to seek a deeper meaning in our lives. The scientific theories discussed in this video may seem complex or difficult to grasp, but they resonate with the spiritual questions humanity has been pondering for millennia. Who are we? Why are we here? What is reality? By exploring these theories, we not only delve into the mysteries of the universe, but also connect with something greater and more profound. These reflections remind us that our perception of reality may be far more limited than we realize, and that behind what our senses allow us to see lies a wondrous and astonishing complexity. This encourages us to open our minds, to embrace the unknown with curiosity and humility, and to recognize that the quest for truth is as much a spiritual journey as it is a scientific exploration. Ultimately, all these reflections serve as a reminder that we are active participants in the universe, capable of contemplating the great mysteries of existence and seeking a deeper purpose. Whether through science or spirituality, the important thing is to keep questioning, exploring, and marveling at the immensity of the cosmos. This video is just one stop on this incredible journey of discovery, a small glimpse into the fact that the universe is vast, mysterious, and full of possibilities that challenge our imagination. Before we conclude, don't forget to like this video and subscribe to our channel if you haven't already. Your support is essential for us to continue bringing more content that expands our understanding of the universe and our connection to it. If you enjoyed what you saw today, I invite you to continue this journey by watching our next video, where we will explore more topics that will surely make you reflect and question what you think you know about reality. See you in the next video. Additionally, I encourage you to delve deeper into your inner journey by downloading our ebook, Divine Essence: Rediscovering the Inner Self and Spiritual Peace. The link is in the description, and this material will help you progress on your path toward balance and inner peace.